So in this talk, I'm going to introduce to report a hidden cost of virtualization when we run multi-core applications in the cloud. So this is a joint work with Phillip Gibbons and Michael Kozuch from Intel Labs. As we know, in multi-core era, we will see more and more cores in the same computer. So the same is also true for virtual machines. So we will see more and more virtual cores in the same virtual machine. For example, IBM EC2 offers instances with 32 cores. Providing more and more virtual cores in the same virtual machine is to satisfy the need of the applications for more cores to improve their performance. For some applications, to use more cores, they need to exploit fine-grained parallelism. So using multiple small virtual machines with a single virtual core may incur prohibitive communication cost because these data exchanges between threads may go through the network stack as I/O operations. Instead, using the virtual cores inside the same bigger virtual machine will be more efficient because threads can exchange data using shared memory. So when we scale applications to use more and more virtual cores in the same virtual machine, a natural question is whether the application can run efficiently in the multi-core virtual machine. Is there any hidden cost? To answer this question, we run applications from Parsec benchmark suite and Splash2x benchmark suite on both physical machines and virtual machines. Then we compare their performance. In the experiment, we keep the number of virtual cores the same as physical cores. So the performance is comparable. So on the right of the slide, in this figure, I show the performance comparison for two representative benchmarks. OceanCP is from Splash2x benchmark suite, and the FaceSim is from Parsec. So with the y-axis, I show the speed up of these applications relative to their single thread performance on physical machine. So we scale the size of the virtual machine from 1 core to 16 cores. When we scale the virtual machine and the physical machine, we see that the performance gap of this benchmarks keeps widening. For example, for OceanCP, the performance gap of its bare metal performance and its performance in the virtual machine keeps widening. When 16 cores is used, the execution time of OceanCP is increased by 123%. So for FaceSim, we see a similar trend. While the slowdown is not as dramatic, the slowdown is still 82% when 16 cores is used. So we were surprised to see so dramatic slowdowns, and we analyzed the causes to understand the performance cost. We find that the Parsec benchmarks and Splash2x benchmarks that suffer most are usually the ones in which the virtual cores are frequently idling due to the block synchronization in the benchmark or in the software system. So when the threads are blocked at a synchronization point, the virtual cores will become idle. The idle virtual cores will be suspended by virtual machine managers so that the physical cores can be allocated to other virtual cores or be put into lower power mode to save energy. So when the condition for the threads to continue their execution is met, we have to wake up the blocked threads to resume their execution. To resume their execution, we first need to activate the virtual cores. Then we activate the blocked threads on these virtual cores. So you may say that the actual cost must be paid every time we switch the status of the virtual core. Please note that it's not enough to just revise the applications to avoid this problem, because synchronization, block synchronization may appear in applications or in libraries in operating systems. Let me use an example to explain what actual cost will be incurred when we wake up threads in virtual machines. So in this thread, we run in this example, we run two threads on two different cores. Oops. One thread calls p thread mutex lock to get a lock to enter critical section. Before it finishes the critical section, the other thread calls p thread mutex lock to get a lock. But because the lock is already held, this thread must be blocked. When the thread holding the lock finishes its computation in the critical section, it calls pthread mutex unlock to release the lock. So the pthread mutex unlock will wake up the thread blocked in pthread mutex lock. So let's look at this part. What operations we must carry out to wake up a thread? If we run these two threads on physical machines, the thread run the physical core running the pthread mutex lock will send rescheduling IPI to the physical core runs pthread mutex lock. IPI stands for interprocessor interrupt. So the interrupt will trigger interrupt handler on the core calling pthread mutex unlock. So the interrupt handler will trigger scheduler to do rescheduling. This is how the thread calls pthread mutex lock can be woken up. If we run these two threads on virtual machine, the IPI cannot be delivered directly to the virtual core calling pthread mutex lock. The virtual machine manager must intercept the interprocessor interrupt to handle it. So the virtual machine manager injects the IPI to the virtual core calling pthread mutex lock. If that virtual core is idle, if it's suspended, the virtual machine manager have to first schedule this virtual core, resume this execution. When this virtual core starts to run, we do rescheduling inside the virtual machine on that virtual core to wake up the thread blocked in pthread mutex lock. So you can see that on physical machine, we must deliver IPIs by hardware. At the same time, we need to reschedule the thread. But if we run the thread on virtual machine, we must deliver the thread by virtual machine manager. That incurs higher cost. At the same time, we must schedule both the virtual core and the thread. That also incur much higher cost. So this cost significantly increase the time to wake up thread in virtual machines. To estimate the cost of scheduling a virtual core and handling IPI, we run the thread in the previous example under different settings. In the first setting, we run the two threads on the same core, either the same physical core on the physical machine or the same virtual core on the virtual machine. Because the thread running on the same core, so we don't need to pay the cost of handling IPI. At the same time, the virtual core is kept active, so we don't need to pay the cost of rescheduling the virtual core. So in this setting, wake up the thread incurs least overhead. So it takes 4 microseconds to wake up a thread on physical machine and 6 microseconds on virtual machine. So the difference is not that large. Under setting B, we run these two threads on two different cores. Because these threads are running on two different cores, we must send IPI to do rescheduling to wake up the thread block that pthread mutex lock. In these settings, we keep the physical core and the physical core active, so we don't need to pay the cost of rescheduling virtual cores. Under this setting, it takes a longer time to wake up the thread. On physical machine, it takes 8 microseconds. On virtual machine, it takes 17 microseconds. So you see that the difference starts to increase. Under setting C, we also run the two threads on two different cores. But the difference is that on the physical machine, if a physical core becomes idle, we put it into lower power mode. If a virtual core becomes idle on a virtual machine, we suspend the execution of the virtual core, and the corresponding physical core will be put into low power mode. So under this setting, we have to pay the cost of handling IPI. At the same time, we have to pay the cost of rescheduling virtual core. So you see that it takes 37 microseconds on virtual machine to wake up the thread. So it's much higher than 17 microseconds. So we can estimate the cost. So it's like 10 microseconds to handling IPI and another 20 microseconds to reschedule the virtual core. So this cost significantly increases the cost to wake up a thread and the cost to do synchronization. To show the correlation between application slowdowns and the frequency at which virtual core transition their status, we select a few benchmarks with different slowdowns and measure the frequency at which the virtual core change their status. We show the slowdown with red bars and frequency with green bars. As we can see with this figure, there appears strong correlation between application slowdowns and the frequency. For dedupe, its execution is slowed down by the largest percentage. At the same time, the virtual cores change their status more frequently than other benchmarks during its execution. For benchmark Black-Scholes and Swapsons, synchronization in these benchmarks are infrequent. So their threads are mostly always busy with useful work so that they keep the cores active. So they incur much fewer state transitions of the virtual cores and the trivial performance slowdown. Based on this analysis, we propose Gleaner as our partial mitigation for this problem. Before I introduce Gleaner, let me survey the possible mitigations for this problem. Because this problem is associated with the status change of virtual cores and the threads. So basically, there are two approaches to reduce the cost. One approach is to reduce the frequency of the status change. The other approach is to reduce the overhead associated with each status change. So let's look at the method to reduce the frequency first. To reduce the frequency, we may use log-free algorithms to avoid synchronization. But log-free algorithms are usually hard to design. Even we have log-free algorithms, they may not be efficient. We may also use spin locks to replace block synchronizations so that we can prevent excessive status changes. But using spin locks may also significantly degrade performance due to the well-known lock holder preemption problem. With a lock holder preemption problem, I mean the thread or the virtual core holding lock is preempted, but other threads or virtual cores requesting lock are scheduled, so they spin there. So this forms a kind of live lock situation. The thread holding lock, it has a lock, but it's waiting for CPU to run. But other thread requesting lock, they spin. They have the CPU, but they wait for the lock. So it's a live lock situation. The live lock significantly degrades performance. To reduce the overhead of the status change, we may let a virtual machine use a special instruction like mwait to put the physical cores into lower power mode. So this method also reduces throughput because a virtual machine may call mwait while other virtual machines are waiting for the physical core to run. So in Gleaner, we use two techniques to improve performance. The first technique is called idleness consolidation. So the basic idea is to consolidate short period idleness into longer period idleness so that we can reduce the frequency of the status change of the virtual cores. So I use this example to explain the basic idea. So with this example, we run two threads on two virtual cores. These two threads collaborate with each other. They synchronize with each other. So the dotted pointers just show the synchronizations. Every time when a thread is blocked at the synchronization point, their idle cores becomes idle, and this virtual cores are suspended. When the condition to resume the execution of the threads is met, we have to wake up the thread. To wake up the thread, we have to pay the high cost to reschedule the virtual core. So the overhead significantly increased the execution time of this application. So with idleness consolidation, we consolidate these two threads onto the same virtual core B. So these two threads execute on virtual core B interleavingly, keep this virtual core busy, active. So we don't need to pay the overhead to change the status of the virtual cores. With idleness consolidation, we want to run the threads on as fewer virtual cores as possible. At the same time, we maintain the parallelism to avoid performance degradation. We suspend other virtual cores so that the corresponding physical cores can be used by other virtual cores or put into lower power mode. To implement idleness consolidation, we dynamically adjust the number of virtual cores that run the application thread based on the workload. If we see the virtual cores, the utilization of active virtual cores drop below a low threshold, we do consolidation. If we see the utilization increase beyond a high threshold, we activate some idle virtual cores and offload some threads to these virtual cores. To detect workload change, we run a yielding thread on each active virtual core. At the same time, the yielding thread keeps the virtual core busy even when the application threads on the virtual core are blocked. A yielding thread is a thread with the lowest possible priority, and keeps calling a scattered yield system call. So they will not block the execution of application thread. The other technique in Gleaner is called IPI-free wakeup. It's to wake up thread without sending IPIs. So this can further reduce the intervention from virtual machine manager. To implement IPI-free wakeup, we can use several mechanisms. The first mechanism is that we call locating the thread, initiate the wake up operation, and the thread being woken up. Or we can put the thread being woken up in the ready thread without rescheduling it immediately. Or we can use exceptions transparent to virtual machine managers like minor page fault to trigger rescheduling, to replace rescheduling IPIs. In Gleaner, we use the first mechanism. To evaluate Gleaner, we implement a prototype. And we run the applications from Parsec 3.0 and Splash 2x in virtual machine. The physical machine has 16 cores, and the virtual machine has 16 virtual cores. The virtual machine is a KVM virtual machine. So on this page, I show the slowdowns of the applications with and without the mechanism in Gleaner. The slowdowns are relative to their bare metal performance. So for the last 4 benchmarks, we see that without Gleaner, their execution is slowed down by large percentages. With Gleaner, with idleness consolidation, the first mechanism, we can significantly reduce the slowdown. With full Gleaner, the idleness consolidation mechanism and the IPI-free mechanism, IPI-free wakeup mechanism, we can further reduce the slowdowns. For the first 2 benchmarks, Black-Scholes and Swapsons, their execution is slowed down by very small percentages. Gleaner will not incur extra overhead, so we can see that the performance of Black-Scholes and Swapsons are similar on the systems without with the mechanism in Gleaners. So that shows that the Gleaners, the overhead of Gleaners is minimal. So as a conclusion, in this work, we show an understudied problem for running multi-core applications in cloud. So this problem is caused by block synchronization in virtual machines. Although there are a lot of works focusing on study the overhead of virtualization, but they focus on I/O operations. This problem causes a significant slowdown even when there's dedicated hardware for virtual machines. So this problem must be solved to run applications efficiently in the cloud. So in this work, we propose a preliminary solution called Gleaner. It uses 2 mechanisms, idleness consolidation and IPI-free wakeup, to reduce the slowdowns of applications in the cloud. Our experimental results show that these 2 mechanisms can reduce the slowdowns significantly for the multi-core applications running in virtual machines. Okay, thank you for your attention, and I'm ready for questions.
Abel Gordon from IBM Research. I was wondering how this work, or if you have considered how future hardware virtualization support for posted interrupts and APIC virtualization will affect the results?
I don't know what kind of hardware support can be provided to solve this problem.
This is hardware support already announced by Intel, what I mentioned.
Ready announced?
Yeah, it's part of the specs.
I think the problem is associated with how you schedule virtual cores. So in Virtual Machine Manager, it wants to take every opportunity to suspend the idle virtual cores so that the resources can be efficiently utilized by other virtual cores, or to put the physical core into low power mode to save energy, right? So if this idea does not change, I don't think hardware support can be used to solve the problem.
So you believe that the fact that posted interrupts and APIC does not require VMM intervention to send, for example, an API will not?
It's not just the API. As I show here, most of our overheads comes from rescheduling of virtual cores, right?
Right.
So it's not just API. Of course, if you use some hardware support to eliminate the cost associated with IPI handling, that definitely helps, but it cannot fundamentally solve this problem.
Okay.
Andy Saylor from the University of Colorado. So your solution doesn't involve actually modifying the VMM or the hypervisor itself, as you've said. And in some ways, it seems like you're kind of trying to outsmart the VMM or the hypervisor, right? I mean, you're right, it wants to make those cores free as quickly as possible because that's in the best interest of Amazon or whoever.
Yeah, I think the other reason is that there's semantic between guest OS and the virtual machine manager, because from the point of view of virtual machine manager, it does not know what's going on inside the guest OS. Right. So it's not very easy to improve the virtual machine manager to solve this problem.
So you don't think you think the appropriate place to solve it is not at the virtual machine manager level, even though right now we're kind of just fighting between the two of them?
I think a complete solution may involve the support from virtual machine manager. But because application and the guest OS has the most knowledge about the behavior of the application, so it's I think the problem can be better solved at the upper level, at the application level or guest OS level. But it may need the support from virtual machine manager.
All right, thank you.
I was just wondering if you maybe consider the baseline approach on your graph without your solution that actually explicitly pin the virtual cores. What will be the performance penalty then?
I think the performance will be worse. So
why? I mean, if I look at this graph here, you say if there is no core rescheduling, then this penalty is not that huge. Why then you think the performance will be worse?
Even if you pin the virtual core on physical core, when the virtual core is idle, you still need to suspend this virtual core so that the virtual core can be put into lower power mode, right, if it's idle.
But isn't this then in conflict with your slides that you're showing right now?
This one?
Yeah.
Why?
No virtual core rescheduling, 17 microseconds, and then...
Oh, this is for setting B. So for setting B, we just keep the physical core active or the virtual core active. So there's no virtual core rescheduling. Okay, I think there's a misunderstanding here. So even if you pin a virtual core on a physical core and there's nothing else, there's no other task running on this physical core, there's still rescheduling because, for example, in Linux, in Linux you have an idle task. Even you don't run other tasks on this physical core, there's still idle task running with this physical core. So there's still rescheduling there.
Thank you.